Imagine this. You're lying back. Maybe it's late at night. Maybe your room is dim, and you can almost hear the quiet hum of the universe outside your window. The stars feel closer than usual. You've always wondered about them. Those glowing dots spread like glitter across a vast black canvas. And tonight, your mind does what it always does when you let it wander. It drifts straight into the question, what if I could just step through space itself? What if I could cheat the distance? That's where the idea of a wormhole comes crashing in. For most people, wormholes sound like science fiction, something cooked up in a movie script or tucked inside a thick physics textbook they'd rather never open. But for you right now, let's strip all of that away. Let's make this simple. Let's make this feel like a story you can hold in your hand. So picture the universe, not as a blurry, endless void, but as something familiar. Think of it as a sheet of paper lying flat on your desk. You've got one dot on one corner of the paper. Let's call that you. On the far side, another dot. That's where you want to go. Maybe it's a star. Maybe it's another galaxy. Maybe it's a place you've only seen through the lens of a telescope. Normally, you'd have to draw a long, straight line between those two dots. That line, that's the journey. That's the years, the light years, the impossible waiting. But then something strange happens. You reach down, and instead of drawing the line, you fold the paper in half. Suddenly, those two dots, they're touching. You didn't erase the distance. You bent reality. And in that bend, right at the meeting point, you've just made a shortcut. That's the wormhole. It's not magic. It's not breaking the laws of physics. It's playing with them. The fabric of space-time, the thing Einstein described in his theory of relativity, isn't just an invisible stage where planets and stars perform. It's flexible, stretchable, foldable, and in theory, puncturable. A wormhole is like a tunnel punched through that folded paper, a passage, a secret bridge between two corners of the cosmos that otherwise would never meet. Now, here's where your brain kicks back and says, wait, that sounds too easy. And you're right. On paper, folding reality sounds simple. In practice, it's a mountain of paradoxes and problems. But hold on. We're not diving into math equations tonight. Not here. Not here. You're not here to sweat through chalkboards full of scribbles. You're here to see it, to feel it, to finally understand it in the easiest way possible. So let's step inside one. Imagine you're standing at the mouth of a glowing tunnel. It doesn't look like a subway entrance, and it doesn't look like some sci-fi blue swirl you've seen on a screen. Instead, it's more like a shimmering bubble, a curved doorway that bends light around its edges. You can see the stars distorted, stretched into spirals like paint dragged by a brush. And beyond the tunnel, impossibly close, is a destination that should have taken you centuries to reach. But here it is, right at the other side. Take a step forward. The space around you stretches like honey pulled thin. There's no wind, no sound, just a hum, low and steady, as if the universe is whispering. You're in the belly of the wormhole now. The tunnel curves, but you don't feel the bend. Space itself is carrying you, guiding you, and then, like that, you're out. And you're somewhere new. That's the dream of a wormhole. But let's anchor this, because science doesn't just run on dreams. Einstein himself hinted at the possibility of wormholes in his equations back in 1935. He and physicist Nathan Rosen described them as Einstein-Rosen bridges. That's the scientific name for the concept, the bridge between 2 points in space-time. Since then, physicists, cosmologists, and even Hollywood writers have wrestled with the idea. Could these bridges exist? Could they be stable? Could they carry a human, or would they collapse faster than you could blink? And here's where your curiosity should spike, because the answer isn't a flat no. The answer is maybe. You see, the math allows it. The rules of relativity don't forbid it. But the catch, the reason wormholes feel like slippery fish in our hands, is that keeping one open would require something exotic, something bizarre, something we don't even know if the universe has: negative energy. Don't worry, we'll get to that. For now, just hold on to the picture: a folded sheet of paper, a tunnel punched through it, a shortcut across the stars. And ask yourself this: why do you even care? Because deep down, you've always hated limits. The speed of light, 186,000 miles per second, sounds fast, but in the scale of the universe, it's nothing. At that speed, at that speed, it would still take you over 4 years to reach the nearest star beyond our sun. Years just to wave hello to Proxima Centauri. And don't even think about Andromeda. That galaxy is 2.5 million years away, even if you could sprint at light speed. That's where wormholes seduce the human imagination. They whisper, you don't have to wait, you don't have to crawl, you can leap. And maybe that's why tonight feels different for you, because you're not just hearing the word wormhole like a buzzword in a physics class. You're finally holding it in your hands. You're seeing the sheet of paper. You're watching it fold. You're stepping into the tunnel. And you're realizing that this impossible, fragile, mind-bending idea is the closest thing we have to a cosmic doorway. So take a breath. We've only just cracked the surface. Ahead of you lies a journey through paradoxes, theories, cinematic dreams, and hard science. By the end, you won't just understand wormholes, you'll feel them in the easiest way possible. And it all starts here. Close your eyes for a second. Imagine you're sitting in a classroom, not the kind with fluorescent lights buzzing overhead, but a classroom made of stars. The blackboard is the night sky itself, and the chalk is the glow of galaxies smeared across the darkness. At the front of this cosmic classroom, you see a man with messy white hair, eyes full of fire, and a mind sharp enough to bend the universe with a pencil. That man, Albert Einstein. And what he's about to show you will change everything. You've probably heard his name tossed around so often that it almost feels ordinary. Einstein equals genius. That's what the world says. But back in 1915, when he published his theory of general relativity, he didn't just write equations. He rewrote reality itself. Here's the easy way to see it. Before Einstein, people thought of space as just a big empty stage, a flat backdrop where stars, planets, and galaxies did their little dance. But Einstein said, no, the stage itself bends. The stage can curve. The stage can twist under the weight of mass and energy. Picture a bowling ball dropped onto a trampoline. The fabric sinks, stretches, curves. Roll a marble nearby, and instead of moving in a straight line, it spirals toward the bowling ball. That's gravity. Not some invisible force pulling from afar, but the bending of the trampoline itself. Now stretch that metaphor to the scale of the universe. Planets, stars, black holes, they're all bowling balls of different sizes, sinking into the cosmic trampoline of space-time. That's what relativity is. That's Einstein's gift. But here's the part nobody told you in school. In the folds of his equations, hiding like a secret door, was the blueprint for something far stranger than gravity. Something he himself may not have fully realized at first. The equations whispered of bridges, shortcuts, hidden tunnels through the fabric of space-time. Fast forward to 1935. Einstein, alongside his colleague Nathan Rosen, takes a closer look. They publish a paper, and in it they describe what we now call an Einstein-Rosen bridge. Imagine two black holes, mirror images of each other, connected by a tunnel. Step into one, and you could, at least in theory, emerge from the other. That tunnel, that's the earliest scientific picture of a wormhole. Now pause. Let your mind chew on that. Because suddenly, wormholes aren't just science fiction. They're written into the same equations that explain how the Earth orbits the sun, how GPS satellites keep time, how the universe itself behaves. Wormholes aren't fantasies. They're mathematical possibilities. But there's always a but. Einstein and Rosen also realized the catch. Their bridge wouldn't last. It would snap shut faster than you could blink. It would collapse before even a single photon of light could sneak through. Like a soap bubble pricked by a needle, gone in an instant. So why does this matter to you? Because even in failure, it planted a seed. The idea that maybe, just maybe, with the right conditions, with the right kind of exotic matter, a wormhole could stay open long enough to travel through, long enough to make the impossible possible. Here's the part you need to feel. Einstein didn't set out to design cosmic highways. He was trying to solve puzzles in his equations. And yet, in the process, he stumbled upon the possibility of shortcuts through reality itself. And think about what that means for you. It means the universe might not be a locked box. It might not force you to crawl at the speed of light for millions of years just to reach another galaxy. It might have cracks, loopholes, back doors waiting to be found. Now, let's bring it down to Earth. Have you ever been stuck in traffic? Horns blaring, cars crawling, minutes ticking into hours? And then, suddenly, you spot a side street, a hidden alley, a shortcut only a few know about. You take it, and in a flash, you're ahead of the jam, free. That rush of skipping the impossible wait, that's exactly what a wormhole promises. Only here, the traffic jam is cosmic, and the shortcut, it's buried inside Einstein's equations. Of course, physicists didn't stop there. Over the decades, others picked up the thread. John Wheeler, the man who actually coined the word wormhole in the 1950s, played with the concept further. He imagined space-time as a frothing, turbulent foam at the tiniest scales, like the surface of boiling water, bubbling with tiny wormholes flickering in and out of existence. They'd be too small, too unstable to ever use. But they showed just how wild reality might be at its roots. And then came the dreamers, the bold ones. Could we scale it up? Could we take the idea from Einstein's chalkboard and stretch it into something real? Something you could walk through? This is where you should lean forward, because the story turns. Physicists started toying with the idea of stabilization, holding a wormhole open with what's called exotic matter. Stuff that doesn't behave like the matter you know. Not like the chair you're sitting on, not like the air in your lungs. Exotic matter would have negative energy density, pushing instead of pulling, acting like a strut to prop the tunnel open. We don't know if it exists in usable amounts. We don't know if it's possible to engineer. But the math, oh, the math leaves the door cracked open. And for you, sitting here tonight, that's enough. Because the easiest way to understand wormholes is this: Einstein gave us the key. His equations are the lockpick. And in that delicate dance of math and imagination, you're not just learning physics, you're glimpsing a hidden architecture of the universe. Think about it. You live in a cosmos where the laws themselves hint at secret passages, where bridges might connect star systems, where shortcuts could leapfrog across galaxies. And that idea doesn't just belong to textbooks. It belongs to you, to your imagination, to your late night wondering. So the next time you see Einstein's wild-haired face on a t-shirt, remember, he wasn't just the man who told us gravity bends space. He was the accidental cartographer of secret tunnels. He drew the first faint sketch of wormholes. And in that sketch lies your first true step toward understanding them. You don't need chalkboards. You don't need a PhD. All you need is the image of a folded sheet of paper, a tunnel connecting 2 points, and Einstein's equations whispering, yes, maybe, just maybe, this could be real. And with that, the secret bridge is yours to cross. You've seen it before, on TV, in a documentary, maybe in a movie. A scientist stands with a sheet of paper in their hand. They put one dot on one side, another dot on the opposite side. They explain, this is point A, this is point B. Normally, you'd have to travel all the way across the paper, and then they fold it, press the dots together, poke a pencil through. There. Shortcut. Wormhole. It's almost too simple, isn't it? The kind of trick a teacher would show in middle school, just to make your jaw drop for a second. But the more you sit with it, the more you realize that simple fold of paper is the single easiest way to grasp the impossible. Because space, for all its vastness, isn't some rigid, unchangeable grid. It's flexible, elastic. And in your mind, that paper becomes a symbol for the whole universe. So let's slow down. Let's make the metaphor breathe. Imagine you're holding a giant map of the cosmos stretched across your lap. Galaxies are little dots sprinkled like crumbs. Your home, the Earth, is one dot tucked inside the swirl of the Milky Way. Now trace your finger outward, past the spirals of stars, across the unimaginable gap to Andromeda, our nearest galactic neighbor. That distance? 2.5 million light years. If you tried to walk it, well, you can't. Even at light speed, it's a journey that outlives civilizations. Empires could rise and fall, whole species could vanish, and still the light wouldn't reach its destination. And yet, with one fold, one simple crease in the fabric of your paper map, you've erased the problem. Suddenly, Andromeda isn't millions of years away. It's just right there, touching your fingertip. That's the essence of wormholes. They cheat distance, not by speeding you up, not by breaking the cosmic speed limit, but by bending the road itself. Here's the beautiful thing. You don't need to wrestle with Einstein's field equations to understand this. All you need is that sheet of paper in your imagination. Because the paper isn't just paper, it's a stand-in for something far bigger. The four-dimensional fabric of space-time. 3 dimensions of space. 1 dimension of time. Together, they're woven like threads in a tapestry. Now imagine tugging on those threads, folding them, punching a tunnel between layers. That's what the paper trick reveals. But wait, your brain probably just whispered a question. If wormholes are just tunnels, why don't we see them everywhere? Good question, because if reality were that easy, you'd expect every galaxy to be linked by shortcuts like a web of glowing highways across the sky. But the truth is far messier. The equations allow them, yes. But nature, she's stingy. She's cautious. If wormholes exist, they're either so tiny they flicker in and out at quantum scales, or so unstable they collapse before anyone could notice. That's why the paper fold isn't just a metaphor. It's also a clue to the problem. Think of it this way. Paper bends easily, but try to punch a tunnel through it with your finger. Unless you reinforce it, the hole tears, the tunnel collapses. The same goes for wormholes. Without something to hold them open, something exotic, they snap shut almost instantly. Still, don't let that dampen your awe, because even as a thought experiment, the paper fold frees you from the prison of distance. And the more you imagine it, the more it reshapes how you see the night sky. Next time you step outside and look up, don't just see stars as unreachable specks. Picture invisible folds between them. Picture tunnels hidden in the blackness, waiting for the right conditions to open. Suddenly, the cosmos feels less like a wall and more like a maze full of secret passageways. And here's the real kicker. The paper trick doesn't just make wormholes easy to picture. It also hints at why they matter so much for you. Because deep down, you're not just curious about space, you're curious about freedom. You hate limits. The thought of being chained by time, by distance, by the sluggish crawl of light across the void, it gnaws at you. Wormholes, even as an idea, give you hope. They whisper, maybe the universe isn't as locked as it looks. Maybe shortcuts exist. And isn't that what you've always wanted, not just in space, but in life? A hidden doorway, a faster way, a leap instead of a crawl. Wormholes echo that craving in your heart. They are the universe's version of what if. Of course, the scientist in you, or maybe just the skeptic, still raises an eyebrow. Fine, the paper fold looks nice, but does it really mean anything? Or is it just a clever trick? Here's the truth. It does mean something. Because that fold represents the exact kind of curvature Einstein described in relativity. It's not just a visual gimmick. It's the literal translation of the math into something your mind can see. Space-time isn't a flat grid. It's a fabric that bends. And in that bending lies the possibility of tunnels. So the next time someone shrugs off wormholes as fantasy, remember, you've seen the trick. You know the paper fold isn't just a classroom stunt. It's the simplest doorway into one of the most profound ideas physics has ever offered. And the best part? You don't need to memorize equations. You don't need to dive into tensors and metrics. All you need to hold on to is that single sheet of paper folded once, pierced through, and you'll always have the easiest way to understand wormholes tucked in your pocket. Because that's what tonight is about, making the impossible simple, making the abstract tangible, letting you feel like the cosmos isn't some foreign land guarded by experts, but a story you can walk into. And in this story, wormholes are your compass, your secret door, your folded paper map of the stars. So hold that paper in your hand a little tighter, trace the dots again, fold, puncture, shortcut, smile, because you right now finally understand what so many struggle to grasp. And the journey? Oh, it's just beginning. Close your eyes again. Not to sleep, though this feels like a dream, but to imagine. Because the best way to understand a wormhole isn't on a chalkboard, it's to walk through one. Picture this. You're standing in space, suit on, visor glowing faintly as you stare at the impossible. Before you is a shimmering sphere, a gateway cut out of the black canvas of the cosmos. It isn't flat like a doorway on Earth. It curves, bulges, almost like a bubble ready to pop. Light bends around its edges. Stars behind it smear into arcs, twisted by the gravity of the tunnel. And in the heart of the bubble, you see something that shouldn't be there, a place impossibly far away waiting for you on the other side. This isn't sci-fi anymore. This is you, stepping into the metaphor you've been building. You take a step closer. The silence of space feels louder now, your own breathing echoing inside your helmet. And then you step through. The moment you enter, it's not chaos, not flashing lights, not a storm of particles. It's smooth. Strange, but smooth. The walls of the wormhole curve around you, like being inside the throat of some vast tunnel. They shimmer faintly, rippling like the surface of oil under sunlight. You don't float, you don't fall. Instead, space itself seems to carry you, pulling you forward as if you were sliding along a hidden current. And here's what you realize. Wormholes aren't about going faster. They're about skipping. You don't beat light. You just don't need to race it. Halfway through, the thought hits you. Where am I, really? Because in this tunnel, you're not in the place you left. You're not in the place you're going. You're somewhere else entirely, in the fold itself, in the crease of the universe. If space is paper, then you are walking through the hole punched between its layers. The hum around you deepens, low and steady, as if the cosmos is humming its own heartbeat. You look ahead, and the tunnel bends, not sharply but gently, curving like a ribbon. You can't see the end, but you feel it. You know something's waiting, and then it happens. The tunnel opens, the shimmer fades, and suddenly you're standing under a new sky. The stars are different. The light is older. The galaxy before you is one you could never have reached in 1,000 lifetimes of travel, and yet here you are, breathing in its glow. That is the promise of wormholes. Not fireworks, not time machines, though we'll get there, but possibility. Now let's step back. Why bother with this visualization? Why imagine tunnels, humming walls, impossible gateways? Because this is how your brain works. You're not a computer crunching equations. You're human. You learn by stories, by pictures, by walking into ideas, and by stepping through this tunnel in your imagination, you finally feel what a wormhole means. But let's sharpen it. Let's connect the metaphor to the science. In Einstein's general relativity, a wormhole isn't just a hole in space, it's a solution, a path through curved geometry. The tunnel you just walked through is described in math by something called a metric, a way of measuring distance and time inside warped space. To physicists, the walls you saw shimmering are actually the structure of that metric, and the smooth glide you felt, that's the curvature carrying you, as space itself reshapes around your journey. It sounds intimidating, but remember, the easiest way to understand it is this. The wormhole isn't an object. It's a place where the rules bend, a crease, a shortcut. But then comes the question you can't shake. Could this ever be real? Could you actually step into a wormhole, not just in imagination, but in reality? And here's the knife edge answer, maybe. but probably not yet. See, the equations allow wormholes, they don't forbid them. But nature is cruel. She doesn't give you tunnels for free. For a wormhole to exist in any stable, traversable way, it would need something holding its throat open, something stronger than gravity's urge to collapse it. That something is exotic matter, matter with negative energy density. Not the kind of matter that makes up stars, planets, or you. Something stranger, something we've only glimpsed hints of in quantum physics. You don't have to know the math, you just have to know this. Without that exotic scaffolding, the tunnel you just walked through would pinch shut instantly, spitting you back into the void, or crushing you before you even entered. And yet, your imagination doesn't care. It walks through anyway. Because sometimes, to understand the frontier of science, you have to live in the tension between what's possible on paper and what's impossible in practice. Think about it. Airplanes were impossible once. So were rockets. So were computers small enough to fit in your pocket. Each began as an idea, fragile, unstable, scoffed at, and yet here you are, living inside their reality. So who's to say wormholes won't follow the same path? That's why you keep imagining. That's why you let yourself walk through tunnels made of folded space. Because imagination isn't just play, it's the rehearsal for discovery. And if you ever doubt that, just remember Einstein himself. He didn't reach relativity by staring at numbers. He got there by daydreaming, by picturing himself riding alongside a beam of light, by imagining strange journeys that no one else dared to take. You're doing the same thing now, walking through wormholes in your mind. And maybe, just maybe, that's where the first real step begins. So, as you stand under this new sky, looking at a galaxy you could never otherwise reach, breathe it in. Feel the awe. Let the impossible feel almost ordinary. Because the easiest way to understand wormholes isn't to treat them like cold equations. It's to live them, to imagine them, to walk their tunnels until they feel real enough to touch. Um, and right now, you've just taken your first journey through one. Section 4 complete. Do you want me to continue into section 5? Keeping the second person documentary tone at 1,000 to 100 words. Section 5, why wormholes feel like cheating the universe, 1,080 words. You've always been told the universe has rules. Gravity pulls, light travels at the ultimate speed limit, time ticks forward, steady and unyielding. These are the laws carved into the very bones of reality. And yet, wormholes sit in the corner, smiling like a trickster, because they don't break the rules, they bend them, they twist them, they let you slip through the cracks like a magician stepping behind the curtain. That's why wormholes feel like cheating. Think about it. Normally, distance is your greatest enemy. Every time you look up at the stars, you're reminded of how trapped you are. Even the nearest neighbor, Proxima Centauri, takes light 4 years to reach. And you'd need tens of thousands of years with current technology, riding in some fragile metal can just to peek at its surface. But a wormhole says, what if you didn't have to? What if you could just skip? It's like standing in line at the grocery store, the queue snaking endlessly forward. You sigh, shuffle, wait, and then someone opens a secret side aisle. You slip through, and in seconds, you're at the cashier, done. Everyone else is still crawling, still waiting. But you've cheated time. That's exactly how a wormhole feels. A cosmic shortcut, a secret alleyway through the fabric of existence. And the best part, it doesn't technically break Einstein's speed limit. Light still moves at the same pace inside the tunnel. You never outrun it. You just take a shorter path. That's the magic. You're not speeding, you're sidestepping. Let's make it sharper. Picture two mountain towns separated by a massive peak. To get from one to the other, you could climb the winding road, switchback after switchback, crawling over ridges and valleys. It takes days, weeks. But then someone builds a tunnel straight through the mountain. Suddenly, the journey isn't days, it's hours. You didn't travel faster, you just didn't have to climb. That's a wormhole, a tunnel through the mountain of space-time itself. And here's the real kicker. You already live in a universe that allows tunnels like this in theory. Einstein's equations don't slam the door shut. They leave it cracked open, whispering, yes, there might be another way. Now, pause for a moment. Ask yourself, why does this matter so much? Why does it stir something inside you? Because you've always hated limits. You've always wanted to believe the walls around you aren't solid, that there's a hidden passage waiting if you're clever enough to find it. Wormholes tap directly into that part of your soul. They're not just physics, they're freedom. Imagine for a second what that freedom would feel like. To step into a tunnel near Earth and walk out near Proxima Centauri, waving at a star 4 light years away as if it were down the street. To visit Andromeda 2.5 million light years distant and be home in time for dinner. To see the edges of the universe itself, not as a dream, but as a destination. You'd no longer be trapped in the small bubble of human reach. You'd be everywhere. Anywhere. The cosmos would shrink into a neighborhood, and you'd finally feel like you belong in it. That's why wormholes feel like cheating, because they undo the harshness of reality. They take the impossible wait times, the suffocating distances, and they toss them aside with a single fold of cosmic paper. But here's the part you can't ignore. Cheating always comes with a cost. Think back to that grocery line shortcut. Sure, you got out faster, but maybe the cashier side aisle doesn't scan properly. Maybe you're accused of skipping. Maybe the system wasn't designed for you to pass that way. The shortcut, tempting as it is, can be dangerous. The same with wormholes. The equations say yes. The imagination says yes, but the reality, it's lined with traps, instability, exotic matter requirements, paradoxes lurking in the shadows, and you as the dreamer have to live in both truths at once. Wormholes are possible and impossible, allowed and forbidden, freedom and fragility. Still, admit it, you love the idea, because it feels like a rebellion, like you're standing up to the cold laws of physics and saying, I refuse to crawl, I will leap. That's why wormholes have burned so brightly in your mind for so long. They're not just equations in dusty journals. They're symbols. Symbols of everything you've ever wanted. Escape, freedom, possibility. Think about how many stories you've seen built on this craving. In movies, wormholes become gateways to other worlds. In books, they're doors to distant galaxies. Even in your own daydreams, they're always there, the escape hatch when the walls close in. And maybe that's the truest way to understand them. Not as guaranteed structures hiding in the void, but as the universe's own metaphor for hope. Wormholes are proof that even the hardest rules might have exceptions, that even the most unyielding barriers might have cracks. And for you right now, that's enough. Because when you stand under the night sky feeling small, wormholes whisper that maybe, just maybe, you don't have to stay small forever. So yes, they feel like cheating. But maybe, just maybe, the universe has always loved a good cheat. Why wormholes collapse before you can use them. You've been soaring with the idea of wormholes, the freedom, the shortcuts, the escape hatch into the stars, and then you hit the wall of reality. Because here's the problem. Wormholes, as beautiful as they sound, are fragile, terrifyingly fragile. The math says they exist, but the same math whispers a cruel twist. Most of them wouldn't survive long enough for you to even step inside. They'd collapse before you could take a single breath. Imagine trying to walk across a frozen lake. At first glance, the ice looks solid, clear, shining, inviting. But the moment you take a step, cracks spider out beneath your feet. The surface groans, and before you can react, you plunge into the freezing water below. That's what wormholes are like. Gorgeous in theory, but unstable in practice. Let's pull back for a second. When you imagine a wormhole, you probably see a tunnel. wide, glowing, stable, like some futuristic highway, a place you could fly a ship through, waving at the cosmic scenery as you pass. But in reality, wormholes, if they exist naturally, are microscopic, tinier than an atom, popping in and out of existence in the quantum foam of space-time itself. They flicker like sparks, vanishing before they can grow. Now here's the heartbreak. Even if one did grow, even if by some miracle it reached a usable size, gravity itself would strangle it shut. The throat of the wormhole would pinch closed faster than light could pass through. The door would slam before you could even see what lay beyond. And that's because gravity is greedy. Remember Einstein's bridge? The fabric of space-time bends under mass and energy. Well, that bending wants balance. It wants to heal itself. And a wormhole is a wound in the fabric, a hole punched through. The universe doesn't like wounds. It wants to stitch them closed immediately. So unless you can fight back against that natural healing force, the wormhole is gone before you can ever call it yours. This is where the dream and the nightmare collide. Because the only way to keep a wormhole open, the only way to fight the crushing weight of gravity, is to use something the universe barely allows: exotic matter. What is exotic matter? It's matter with negative energy density, negative mass, a substance so strange it defies your normal sense of reality. Instead of pulling things in with gravity, it would push them away. Instead of collapsing space, it would hold it open. Think of it like scaffolding. If a wormhole is a tunnel trying to collapse, exotic matter is the steel framework that braces the walls. Without it, the tunnel caves in instantly. With it, you might, just might, keep the passage stable long enough to walk through. But here's the kicker. No one knows if exotic matter even exists in the amounts you'd need. Some hints suggest it's possible, like the Casimir effect, where tiny quantum forces between plates mimic negative energy. But those effects are microscopic, barely measurable. To hold a wormhole open for a spaceship, you'd need mountains of the stuff, oceans of it. And right now, you don't even have a teaspoon. This is the heartbreak of wormholes. The theory gives you everything: the freedom, the shortcut, the rebellion. And then the reality takes it back, whispering, "Not so fast, not without a price." But here's what you love about this moment. You realize science is honest about its limits. It doesn't lie to you. It says, we don't know. Maybe yes, maybe no. And that uncertainty, it keeps the dream alive, because as long as it's not impossible, it's worth chasing. Now pause and let that sink in. Think about how many times humanity has faced this exact wall. Heavier than air flight? Impossible, they said. Harnessing electricity? Impossible. Landing on the moon? Impossible. Every great leap begins with a chorus of doubt, and every time someone stubborn enough says, "We'll see." That's where you stand with wormholes. On the edge of a cliff, staring down into the impossible, daring to imagine scaffolding made of negative energy holding a doorway through space-time open. Of course, the risks don't stop there. Even if you stabilize a wormhole, like even if you brace it with exotic matter, you face new dangers. Radiation could flood through the tunnel, heating it to destruction. Tiny fluctuations could ripple and amplify, shredding the passage like tissue paper. A single misstep and the bridge collapses with you inside. Still, you can't let go of the hope, because for every risk, there's a what if. What if exotic matter isn't as rare as you think? What if the universe hides it in corners you haven't searched? What if future physics cracks the code, turning the impossible into the ordinary? After all, once splitting the atom was fantasy. Now it's history. Once walking on another world was myth. Now it's memory. So why not wormholes? You breathe deep, letting the truth settle. Wormholes are fragile. They collapse. They resist your attempts to use them. But even in that fragility, you see a spark of possibility. Because sometimes the most fragile ideas turn out to be the ones that change everything. And that's the fragile truth. You can't walk through wormholes today, but you can imagine them. You can study them. You can prepare for the day when fragile becomes stable and impossible becomes real. So, yes, wormholes collapse. Yes, they demand a price you can't yet pay. But isn't that exactly what makes them worth dreaming about? Because if the door to the universe were easy, wouldn't it already be open? You're standing at the edge of the impossible, staring at a doorway that collapses before you can even touch it. Wormholes are fragile, too fragile, unless you find a key. And the universe whispers that key's name: negative energy. Now, don't confuse this with negativity in your life, the bad days, the doubts, the failures. This isn't about emotion. This is about physics, a type of energy that doesn't just resist gravity, but reverses it, a force that doesn't pull, it pushes, a substance that doesn't weigh down reality, but props it open like invisible scaffolding. You already know normal matter. It's everything you touch: atoms, molecules, planets, stars. All of it has mass. All of it bends space-time downward, inward, squeezing it like a hand pressing into soft clay. That's why wormholes collapse, because all the matter around them presses down until the tunnel caves shut. But negative energy, it does the opposite. Imagine a hand pulling up on that same clay, stretching it, holding the dent open instead of letting it heal. That's what exotic matter could do for a wormhole. Brace the throat, keep it wide, stop gravity's relentless grip. It sounds insane, doesn't it? Matter with negative mass. If you pushed it, it would accelerate toward you instead of away. If you dropped it, it would fall upward. Everything about it seems backwards, broken, like physics seen in a mirror. And yet, Einstein's equations allow it. The math doesn't forbid negative energy. In fact, tiny glimpses of it already shimmer at the edges of your experiments. Think of the Casimir effect. Two metal plates placed incredibly close together in a vacuum. Quantum physics says the vacuum isn't empty. It seethes with fluctuations, particles flickering in and out of existence. But between those plates, certain fluctuations can't exist. The energy outside is greater than the energy inside. The result? The plates are pushed together by what seems like a negative pressure. It's tiny, microscopic, but it's real. A hint that negative energy isn't pure fantasy. It's lurking in the fabric of reality itself. Now imagine scaling that up. Not just plates in a lab, but oceans of exotic matter. Enough to line the walls of a wormhole, enough to push outward against the crushing weight of space-time. Suddenly, the impossible begins to look like scaffolding for the future. Here's the image that sticks in your head: a tunnel through the universe, its throat glowing not with ordinary light, but with the shimmer of exotic energy, negative pressure holding it open like the ribs of some cosmic cathedral. You step inside, and for once the passage doesn't collapse. For once the dream holds. But don't let yourself get carried away too quickly, because exotic matter is slippery. You don't have it. You don't even know if you can have it in the amounts required. And even if you could harvest it, how would you handle it? Would it be stable? Dangerous? Would it unravel ordinary matter, tear apart anything it touched? Or could it be tamed, shaped, engineered like steel? This is the razor's edge of wormhole physics. Exotic matter is the key, but it's also the question mark hanging over everything. Without it, wormholes collapse. With it, they may hold. But the gulf between may and will is enormous. Still, the thought burns in you. If exotic matter exists, then wormholes are not just science fiction. They're engineering problems. And engineering problems, humanity has a habit of solving them. Think of the first powered flight. Before the Wright brothers, heavier-than-air machines were dismissed as ridiculous. But once the physics was understood, once the materials were ready, the leap came fast. Planes filled the skies within decades. Think of nuclear energy. For centuries, atoms were untouchable mysteries. And then suddenly, the equations split open, and the power of the sun was in human hands. So imagine the same arc for exotic matter. From theory to experiment, from experiment to control, from control to construction. And one day, not so far away, engineers weld the ribs of negative energy into the throat of a wormhole, locking it open like a gate. And you, yes you, step through. Now pause here. Let yourself feel both sides of the truth, the hope and the hesitation. On one side, wormholes are impossible without exotic matter. On the other, exotic matter may already be woven into the fabric of the universe, waiting for you to learn how to use it. This is the paradox of science. You live in uncertainty. You dream in maybes. But those maybes, they're fuel. They're what keep you pushing forward, what keep you looking at the stars and thinking, what if? So here you stand, holding the exotic key in your imagination, a key you don't yet know how to forge, but one you believe could exist. And that belief alone cracks open the door to the future. Because if exotic matter is real, and if humanity finds a way to use it, then wormholes shift from fragile dreams into possible highways. The universe shrinks, distances collapse, and for the first time, the stars stop being unreachable pinpricks and start being neighbors. That's the promise of the exotic key. And though it remains out of reach, you can feel it glowing in the dark like a torch waiting to be lifted. You thought wormholes were just about distance, shortcuts through space, a way to visit stars, galaxies, whole corners of the cosmos you never dreamed you'd see. But then you realize something far stranger. Wormholes don't just mess with where you are, they mess with when you are. Time and space aren't separate. Einstein taught you that long ago. They're woven together in a single fabric, space-time. Bend one and you bend the other. Stretch one and the other stretches too. That means every wormhole is not only a tunnel through space, it's also a tunnel through time. Let that sink in. You're not just stepping into another place. You could be stepping into another moment. Here's how it works. Picture two mouths of a wormhole, two doorways connected by the tunnel. Now imagine moving one mouth, dragging it near something massive, or accelerating it close to light speed. Because of relativity, time flows differently at each mouth. One stays normal, ticking away at the usual rate. The other experiences time more slowly. You've seen this before in the famous twin paradox. One twin stays on Earth, the other travels near the speed of light and comes back younger. Time ran slower for the traveler. Now, apply that to wormholes. If one mouth sits in a high-speed spaceship or near a black hole while the other stays far away, their clocks tick out of sync. But remember, the mouths are still connected. The tunnel links them directly, ignoring the vast distance outside. So when you step in one mouth, you don't just arrive somewhere else. You arrive someone else. Maybe it's the future. Maybe it's the past. Maybe it's both, depending on which way you walk. And suddenly, wormholes stop being just shortcuts. They become time machines. The thought sends shivers down your spine. You always imagine time travel as fantasy, flux capacitors, spinning police boxes, clocks striking midnight. But here it is, hidden in the logic of relativity. No magic, no fiction, just geometry. Of course, the consequences are enormous. Time is delicate. You've always felt it as one steady river, flowing forward, never back. Wormholes throw a rock into that river, splashing waves in every direction. Imagine this. You walk into a wormhole today, 2025. You step out the other side and it's the year 2085, 80 years gone in an instant. Your friends, your family, your world, all aged, changed, maybe gone. For you, it was a step. For them, it was a lifetime. You walk in, and on the other side, it's 1965. A past you've only read about, suddenly alive before your eyes. You breathe the air, hear the voices, touch the fabric of history itself. But then, the paradoxes creep in. If you can travel to the past, what happens if you change something? Meet yourself? Alter history? The classic grandfather paradox haunts you. What if you erase the conditions that let you travel back in the first place? And what if others used wormholes for time travel? What if civilizations built networks of them, stepping not just across galaxies, but across centuries? Would history even make sense, or would it twist, loop, knot itself into impossible shapes? It's dizzying, beautiful, terrifying, and yet you can't look away, because deep down you've always wanted more than space travel. You've wanted freedom from time itself. You've wanted to slip out of the river to see where it begins and ends. Wormholes dangle that possibility in front of you like a forbidden fruit. Of course, not everyone agrees it's possible. Some physicists argue that the universe would protect itself, that wormholes allowing time travel would collapse under their own paradoxes, that radiation would flood them, destroying the tunnel before you could use it. But others whisper, maybe not. Maybe the universe is stranger than you think. Maybe time travel isn't forbidden, just waiting for the right doorway. And you're caught in the middle, excited, anxious, thrilled by the dream, chilled by the danger. So you picture it. You close your eyes and imagine stepping through a wormhole and seeing the clock spin wildly, the sky change, the world morph. You imagine shaking hands with your future self or whispering advice to your past. You imagine standing outside of time all together, watching centuries pass like waves on the shore. For a moment, it feels real. For a moment, you're not trapped in the steady march of seconds. You're free. And then you open your eyes and you're still here, in this moment, bound by the clock on the wall. But your mind is different now, because you've seen how wormholes aren't just cracks in space, they're cracks in time. And once you've seen that, you can't go back. Because now, every time you look at the stars, you don't just wonder what worlds are out there. You wonder when they are. You wonder if wormholes don't just connect places, but eras. If the future and past aren't sealed away, but waiting at the other end of some hidden tunnel, it changes everything. So yes, wormholes may be unstable, they may require exotic matter, they may remain for now fragile dreams, but in your heart, you already know. If they exist, they won't just rewrite how you travel. They'll rewrite how you understand time itself. And maybe, just maybe, that's the most radical promise of all. You've probably heard the word wormhole before. Maybe it was in a science fiction movie, maybe it came up in a late night conversation with friends, or maybe you stumbled across it while scrolling through some cosmic video online. And every time it felt the same, fascinating, yet strangely out of reach, like a secret door in physics that you knew was there, but you could never quite step through. And honestly, that's the problem, isn't it? For decades, wormholes have been wrapped up in this thick fog of jargon, equations, and abstract thought experiments. You've heard phrases like Einstein-Rosen bridge or shortcut through spacetime, but it never really clicked. You nodded your head, pretended you understood, and deep down you thought, wait, what does that even mean? But today, you're not just skimming the surface. Today, you're finally walking through that door, because I'm going to show you the easiest way to understand wormholes. Not with endless math, not with dizzying equations, but with simple, clear human language. The kind of language that makes your brain sigh in relief and say, ah, now it makes sense. So let's start from the very beginning. Imagine space-time, the very fabric of the universe, as a giant sheet. Not a flat, boring sheet, but a flexible, stretchable one, like a trampoline. Every planet, star, and galaxy sits on this sheet, pressing into it, bending it. That bending is what we call gravity. Simple enough, right? The Earth bends space-time, the moon feels the bend, and that's why it orbits. Now picture this. Instead of walking across the sheet from one side to the other, what if you could fold it? What if you took two distant points on that sheet and bent them until they touched? Suddenly, a trip that should have taken thousands of years becomes just one small step. That's the essence of a wormhole, a bridge, a tunnel, a cosmic shortcut connecting two far apart places. But here's where people usually get lost. They think of wormholes like magic doors. They imagine stepping into one and instantly popping out somewhere else, like teleportation. But wormholes aren't magic. They're not cheats. They're geometry. They're what happens when space-time itself curves so dramatically that it folds in on itself, linking 2 points. The easiest way to picture it, think of an ant crawling